These are your notes for Unit 4, Day 1A, or the first day of second semester. If you would like to see the warm-up, review question, or any test questions we went over in class today, just look at the finished notes. All right, so today we're going to do some review of first semester, and then I'll intro our idea for the start of second semester called integration, and we're going to start with something called Riemann sums. So we're just going to start, though, by reviewing how to do limits and derivatives. So a quick review of limits. So let's see what we can remember about taking different types of limits. So let's look at this first one. The limit as x goes to negative infinity of 5x squared minus 3x minus 4 all over 2x minus 3 squared. So if you remember, a limit that's going to an infinity is asking about the end behavior on the graph. So it's asking, as I'm getting really close to the left side of the graph or really close to the right side of the graph, what are the tails of the graph doing? So what's the graph doing? Is it shooting up to infinity, down to negative infinity? Is it leveling off at a number? So as I'm approaching negative infinity, it's end behavior on the graph on the left side. So what's happening on the left side of the graph as my x values get really, really large? Well, if you notice, the numerator and the denominator are both polynomials. And so you can use the degree war on these problems. So you look for the highest degree in the numerator and the highest degree in the denominator. Well, the highest degree in the numerator would be the x squared. So you have 5x squared is the term I'm going to be looking at in the numerator. And then in the denominator, we're actually going to have to multiply this out to see what's happening. So 2x minus 3 squared means 2x minus 3 times 2x minus 3. And the term that would have the highest exponent, because that's really the only one that I need to multiply out, would be 4x squared. So now if I look at this, I have 5x squared over 4x squared. So remember, if it's a tie, so the highest degree in the numerator is 2 and the highest degree in the denominator is 2, it's a tie. So when it's a tie, the limit as x goes to infinity or x goes to negative infinity is going to be the fraction of their leading coefficients. So this limit is going to be 5 over 4. So if I were to pull up the graph of this, as my x values get farther and farther to the left, my y values are approaching a height of 5/4 or 1.25. All right, on the next one, it wants the limit as x goes to 0, and then remember that little negative sign up top means from the left. So as I'm approaching 0 from the left side of the graph, what are my y values doing? Well, your first step on any limit problem, if it's not infinity, is to plug it in. So if I take 0 and plug it into the x's, I get 0 over 0. So at this point in time, you've got two options. You have an indeterminate form of 0 over 0. So you can either use L'Hopital's rule, or you can come up with a common denominator in the numerator and then simplify the fractions. I will do it both ways. So let's start with the common denominator method. So 1 and then x plus 6 is in the denominator, minus 1 over x plus 6. So the common denominator, I've got to multiply the two denominators by each other. So this fraction needs to get multiplied by 6, and this fraction needs to get multiplied by x plus 6. And so I have 6 minus x plus 6 all over 6 times x plus 6, and then all over x. And so if I simplify this, I'll distribute that, and I would get 6 minus 6 goes away, so I have negative x over 6 times x plus 6, and then divided by x. And remember, dividing by x is the same thing as multiplying by 1 over x. So I have negative x times 6 times x plus 6 times 1 over x. Those x's will end up reducing with each other. And so I'm left with negative 1 over 6 times x plus 6. And now I want the limit as x goes to 0 from the left. Well, we plug in, and if I take 0 and plug it in, I get negative 1 over 36. So that is getting a common denominator and simplifying it that way. Your other option is L'Hopital's rule, and using L'Hopital's rule, you would take the derivative of the numerator over the derivative of the denominator and then take the limit again. So if I took the derivative of the numerator, well, the only thing that I would have to take the derivative of is 1 over x plus 6, because the derivative of 1 over 6 is 0. And then the derivative of x in the denominator is just 1. So when I take the derivative of the numerator, I'm going to use quotient rule. So derivative of the top is 0 times the bottom minus the derivative of the bottom is 1 times the top is 1 all over the bottom squared. And so if I simplify this, I get the limit as x goes to 0 from the left. And in the numerator, I get -1. And in the denominator, I get x plus 6 squared. And then all over 1 doesn't do anything. So then I'm going to plug in the 0. And if I plug in the 0, I get -1 over 6 squared, which is -1 over 36. So even if you use the common denominator method, or if you use L'Hopital's rule, you get the same answer. All right, let's look at the next one. So the limit as x goes to 3, and that little plus sign means from the right. So as you're approaching 3 on the right-hand side, what's happening to the graph? So your first step on any limit problem is plug in the 3. So if I plug in the 3, I would get 27 minus 1 over 9 minus 9. So I get 26 over 0. Now that is undefined. So now I have to think about it as I'm approaching 3 from the right-hand side. So instead of plugging in 3, I'm going to plug in a number on the right-hand side of 3 that's close to 3. So I'm going to plug in like 3.1 or 3.01. And then remember what that means. If I get 0 in the denominator, that means that I'm going to have a vertical asymptote on the graph. So I have a vertical asymptote on the graph at 3, which means that either the graph is shooting up to infinity or down to -infinity. So I want to know what's happening on the right-hand side. Is it shooting up to infinity or down to -infinity? So again, in order to figure that out, I'm going to take a number close to 3. So let's do like 3.1 and plug it in. So if I take 3.1 and plug it into the numerator, I'll get positive answers. And if I take 3.1 and plug it into the denominator, I get positive answers. And a positive over a positive is positive. So that means that this graph on the right-hand side of 3 will be approaching positive infinity. All right, let's look at the next one. Again, I have a limit as I'm approaching -infinity. So a -infinity, and they're both polynomials, so I can do the degree war. So if I look at the degree war, who wins? The degree of the numerator is 3. The degree of the denominator is 2. So the numerator wins. When the numerator wins, remember it's infinity or -infinity, and you've got to decide which one it is. So you take your x value and plug it in. So I'm going to take -infinity. If I plug it into x squared, -infinity squared is positive infinity, but then that negative makes it negative. So my denominator will be negative. If I take -infinity and plug it into the numerator, -infinity cubed would be a negative, and a negative over a negative would be positive. So that limit would be positive infinity. All right, let's look at our next one up here. So I'm approaching -infinity again, and both of those are polynomials, so I could do the degree war. And again, it's a tie. I have x squared over x squared, so it's the leading coefficient, so it'll be 17 over 36. If the denominator wins, remember the limit would be 0. There's not an example of one of those, but on the next one, take 2 and plug it into the numerator and the denominator, and I would get 8 minus 16 over 0. So again, that's undefined, and since I'm not approaching from the left or the right, this limit would not exist. So the only way you can talk about a limit if you get 0 in the denominator and not the numerator is if you're approaching from the left or approaching from the right. So those are limits algebraically. All right, let's talk about limits graphically. So let's look at A. The limit as x is approaching -3 from the left of my graph. So here's -3. As I'm approaching -3 on the left-hand side, what is my graph approaching? Well, it's approaching a height of 4. On the next one, it says -3 from the right. So B says, what's happening as I'm approaching -3 on the right-hand side of -3? Well, here's approaching -3 on the right-hand side, and that's also at a height of 4. C wants to know what is the actual value of f at -3. So that's going to be this dot up here. Because notice down here, it's a hole, so that's not my function value. The function of value occurs at the closed dot, and that's at a height of 8. The next one says, what's the limit as I'm approaching 1? And notice there's not a plus or a minus, so it means on both sides of 1. So here's 1. As I'm approaching 1 on both sides, I'm at a height of 2. And then the next one wants to know, as I'm approaching 2, what's the limit? So here's 2. As I'm approaching 2 on both sides of 2, I'm at a height of 1. It wants to know what's my function value at 2. Well, at 2, there's an open circle and there's no closed circle. So there is no function value at 2. It wants to know what's the limit as I'm approaching 4. So on the right-hand side, my limit looks to be positive 1, but on the left-hand side, it looks to be negative infinity. Since those two limits don't match up, the limit does not exist. Next one wants to know, as I'm approaching positive infinity, what's my limit? Well, positive infinity is asking for what's this tail doing. That tail on the right-hand side of the graph is shooting up to positive infinity. And then my last one says, what's happening as I'm approaching negative infinity? Well, negative infinity is that left tail, and my left tail is approaching a height of 5. And so those are examples of limits graphically. All right, let's review our derivative rules. So given f of x is 2 over the square root of x minus 5 times the 4th root of x plus 12x to the 3rd minus 4 pi plus 6.5x, find f prime of x. So this is just an example of power rule because you just have a whole bunch of polynomials. So let's rewrite this function first so we can see all these exponents. So this would be 2x to the negative 1/2 minus 5x to the 1/4 plus 12x to the 3rd minus 4 pi plus 6.5x. Now to take the derivative using power rule, remember you multiply by the exponent and then subtract 1 from the exponent. So it would be 2 times negative 1/2, which is negative 1, and then subtract 1 from the exponent, and you would get negative 3/2. So the derivative of the first term is negative x to the negative 3/2 power. The next term, multiply by the exponent, and you get negative 5/4. Subtract 1 from the exponent, and you get negative 3/4. So the derivative of the next term would be negative 5 over 4 x to the negative 3/4 power. The derivative of the next term, 12 times 3 is 36, and then subtract 1 from the exponent, you get x squared. Negative 4 pi is a constant. I know it looks weird, but it's a constant, so the derivative of a constant is 0. And then plus 6.5x, the derivative of 6.5x is just 6.5. So that would be the derivative of that function. And remember, derivatives are the slope of the tangent line. All right, for 2, find dy over dx. Again, that's just another way of saying the derivative. And so I'm going to rewrite this as 5x to the 3rd minus 2x plus 9 pi, and that's going to be to the 1/4 power. So y prime, or dy dx, we're going to use chain rule. So this is going to be chain rule. And so remember, for chain rule, you multiply by the exponent. Well, the outside function is the 1/4, so we're going to take the derivative of the outside function, so that's power rule. So multiply by the exponent, and then for chain rule, you leave the inside alone, and then you multiply by the derivative of the exponent, so, well, subtract 1 from the exponent, so negative 3/4. And then for chain rule, you multiply by the derivative of the inside function, so it would be 15x squared minus 2, because again, 9 pi is a constant. And that would be the derivative, or the slope of the tangent line, for that function. Next one, we're going to use product and chain rule. So remember, product rule says take the derivative of the first function, which is x to the 3rd. Then you leave the second function alone. And then you take the derivative of the second function and then leave the first function alone. So g prime of x is going to be the derivative of the first function is 3x squared. Then you leave the second function alone, x squared minus 7 to the 5th. Then in the middle of the product rule is plus, and then take the derivative of the second function. So I'm going to use chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. And then don't forget, for product rule, then you multiply by the first function. So we have, this is f, this is f prime, this is f, and then this is g, this is g, and this is g prime. So we have f prime g plus g prime f. All right, in our next one, we can use quotient rule. So quotient rule says take the derivative of the numerator, leave the denominator alone, minus derivative of the denominator, leave the numerator alone, all over the denominator squared. So dy over dx is going to be the derivative of the numerator is 1, then leave the denominator alone, then minus the denominator, if I rewrote it, would be 3 minus 4x to the third to the 1/2 power. So I'm going to use chain rule. So derivative of the outside, leave the inside alone, times the derivative of the inside, so negative 12x squared. So that's the derivative of the denominator, then times leave the numerator alone, then all over the denominator squared. So if you square a square root, it goes away, or we can just write it. So 3 minus 4x cubed square rooted squared. And so that would be the derivative using quotient rule for that function. And then our next one is implicit differentiation. So for that first term, 4y to the third x squared, our first term is 4y cubed, and then for product rule, the second term is x squared. So we're going to use product rule right here. So product rule says take the derivative of the first term. The derivative of 4y to the third is 12y squared, but it's implicit. So remember, whenever you take the derivative of a y, you multiply by dy over dx. So that's the derivative of the first, then times leave the second alone. Then for product rule plus, you take the derivative of the second, which is 2x, then times leave the first alone, 4y cubed. And so this would be the derivative of that first term. Okay, and then minus the derivative of negative 4y would be negative 4, and then the derivative of y is dy over dx. Then plus the derivative of 5 is 0 equals the derivative of x is 1. And now let's simplify this. I can multiply the 12y squared and the x squared to get 12x squared y squared, and then dy dx. And then I can multiply the 2x and the 4y cubed, and I would get 8xy cubed, then minus 4 dy over dx equals 1. I'm going to keep the dy dx's on that term, so I'm going to move the 8xy to the third to the other side, so I'm going to subtract it. And so I get 12x squared y squared dy over dx minus 4 dy over dx equals 1 minus 8xy to the third. Now I can factor out a dy over dx from both of those terms, and I get 12x squared y squared minus 4 equals 1 minus 8xy to the third. Then divide both sides by the 12x squared y squared minus 4. And so the derivative, dy over dx, using implicit, would be 1 minus 8xy to the third, all over 12x squared y squared minus 4. And that would be the derivative of that relation using implicit differentiation. So this is implicit differentiation. All right, so let's put some of these ideas together in a different looking type of problem. So the graphs of f and g are shown below. Let h of x be g of f of x. So this would be like a chain rule problem. And let p of x be g of x over f of x. So this would be a quotient rule type of problem. And let q of x be f of x times g of x. So this would be a product rule type of problem. So for A, it wanted us to find q prime at 3. Well, let's start by finding q prime at x. Well, q is right here, so we're going to have to use product rule to find q. So product rule says take the derivative of the first, so f prime of x, times, leave the second alone, so times g of x, then plus take the derivative of the second, g prime of x, then times, leave the first alone, f of x. And now I want to find all of those values at 3. So I want to find f prime at 3, and then I'm going to multiply it by g at 3. Then I'm going to find g prime at 3, and I'm going to multiply it by f at 3. So let's go ahead and look down at this graph. So we're looking right here because here's 3. So I'm looking at all these values at 3. F prime at 3, well, f prime at 3 means the slope of that line at x equals 3. So I want to find the slope of that line. So let's zoom in and see if we can figure out the slope of this line. It looks like I started at the point negative 3, 6, and I ended at the point 0.99. So it looks like it ended up at the 0.99, and I started here at the point -3.6. So the slope, it looks like I went up 3 and over 12. So that slope looks like I went up 3 and over 12. So the slope of that line is going to be 3 over 12, or 1/4. So f prime at 3 is going to be 1/4, because that's going to be the slope of that line. And now it wants g at 3. So it just wants the value of g at 3. Well, this function is g, and so g at 3 is that point right there, which looks to be -3. So I'm going to do -3. Then plus, now I want g prime at 3. So I want to know the slope of g at 3. Uh-oh. Notice that the tangent lines at 3 are coming in two opposite directions, or you have a corner here. When you have a corner, the derivative does not exist. So g prime at 3 does not exist. And let's just keep finding that last one. F at 3 would be right here, and that looks to be 7.5, so times 7.5. But since one of the terms does not exist, q prime at 3 is not going to exist, so that whole problem does not exist. All right, let's look at that next one. P prime at -1. So P is going to be this function right here. So we're going to use quotient rule. So P prime of x, using quotient rule, would be the derivative of the top, which would be g prime of x, then times the bottom, f of x, then minus the derivative of the bottom, f prime at x, times the derivative, or sorry, times the top, g of x, all over the denominator squared. So f of x squared. All right, so now they want us to find it at -1. So we're going to plug -1 into all of these. So g prime at -1 times f at -1 minus f prime at -1 times g at -1 all over f at -1 squared. All right, so let's plug into that. So -1 is right here. So let's find g prime at -1 would be the slope of this line right here. Well, let's zoom in and find the slope of that line. So this right here is the point -5, 5. And then down here is the point 3, -3. So to find the slope of that line I went down 8 and over 8. So that would have a slope of -1. So g prime at -1 is -1. Then it wants f at -1. Well, f at -1 would be right here, which looks to be 6.5. And then minus f prime at -1. Well, we've already found the slope of that line. The slope of that line was 1/4. And then g at -1. So g at -1 is right here, which looks to be +1. And then all over f at -1 squared. Well, f at -1 was 6.5, so that would be 6.5 squared. And then you can simplify that if you want to. But that would be p prime at -1. All right, let's find h prime at -6. So we're going to do, h is the chain rule problem. So chain rule says, so h prime of x would be the derivative of the outside, so g prime, leave the inside alone, f of x, then times the derivative of the inside, so f prime of x. We want to find this at -6, so this would be g prime at f of -6, then times f prime at -6. So we're going to look at -6 now. So -6 is right here. So we need to start by finding f at -6. So f at -6, so this is my f function right here. F at -6 is 1. So now I need g prime at 1 times f prime at -6. So f prime at -6 would be the slope of this line right here. Well, this is the point -10, 5. And then this is the point -5, 0. So that line looks to have a slope of down 5 over 5. So that's going to be a slope of -1. So f prime at -6 is -1. And then g prime at -6, well, that would be the slope right here. And the slope of that line, since it's a flat line, would be 0. So h prime at -6 is going to be 0 times -1, which is 0. so let's review tangent lines now. So given the function f of x equals x over x minus 3, find the equation of the tangent line of the curve at x equals 4. So remember, to find the equation of a tangent line, we need y minus y1 equals m times x minus x1, where this m is going to be the derivative at the x value that we want. So we want to find the derivative at 4. So first, let's find the derivative. We'll use quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. And then we want to find the slope of the tangent line at 4, so let's plug 4 in. So 1 times 4 minus 3 minus 1 times 4, all over 4 minus 3 squared. So this would be 1 minus 3 over 1. So the slope, 1 minus 4 over 1. So the slope of my tangent line would be negative 3. We also need to know the function value at 4. So we're going to plug 4 into the original function. So this would be 4 over 4 minus 3, which would be 1. So I have a slope of negative 3, and I have a point of 4, 1. So the equation for my tangent line when x is equal to 4 is going to be y minus 1 equals negative 3 times x minus 4. All right. Find the equation of the tangent line to the curve when the slope is equal to negative 3/4. So we want the slope of the tangent line to be equal to negative 3/4. Well, the slope of the tangent line is the derivative, so we want the derivative to be equal to negative 3/4. Well, my derivative was 1 times x minus 3 minus 1 times x, all over x minus 3 squared, and I want that to equal to negative 3/4. Well, I'm just going to cross multiply here. And so I get negative 3 times x minus 3 squared equals 4 times x minus 3 minus x. So I've got negative 3 times x minus 3 squared equals negative 12. I'm going to divide both sides by negative 3. And so I have x minus 3 squared equals 4. I'm going to take the square root of both sides. And so I get x minus 3 equals positive or negative 2. So we'll do both solutions. So x minus 3 equals positive 2 or x minus 3 equals negative 2. So either x is equal to 5 or x is equal to 1. So it said find the equation of the tangent line when x is equal to negative 3/4. Okay, well, we know that the two x values that we want are 5 and 1. So to write the equation of a tangent line, we need the slope, which is negative 3/4. And we also need the x value and the y value. So to find the y values that match up, we're going to plug in. So f at 5 is going to be 5 over 5 minus 3, which would be 5 halves. So this tangent line would be y minus 5 halves equals negative 3/4 times x minus 5. So that would be one equation of the tangent line when the slope is negative 3/4. And then if x is 1, f at 1 is going to be 1 over 1 minus 3, which is going to be negative 1/2. So that tangent line would be y plus 1/2 equals negative 3/4 times x minus 1. So those would be the two equations of the tangent line when the slope is negative 3/4. All right, so now let's kind of just introduce where we're going this semester. So we reviewed some basic concepts from last semester. Let's do some intro to this semester. So let's start with derivatives. So graphically, what we've been doing when we've been finding derivatives, like if this is our picture, and let's just say this is C, what we've been doing is we've been taking a tangent line and we've been putting it on our curve, and then the derivative is the slope of the tangent line, right? Or if you take a derivative of displacement, you're given velocity. So it's a rate of change, right? And a derivative is the instantaneous rate of change. So it's how fast you're going exactly at that point C. This unit, instead of finding rates of change, what we're going to do is we're going to find the area under the curve. So that's what an integral is. It's going to be the area under the curve. So it's going to be in between the curve and the x-axis. So we're finding the area under the curve. And it's going to be bounded by the curve and the x-axis. So we're moving away from slopes of tangent lines or instantaneous rates of change, and instead we're going to try and find areas. So what does that mean? If you go backwards, so if you have a derivative and then you undo it, or you do the inverse of it, you get back to the original. So if you undo a derivative, so if you undo f prime of x, you get back to f of x. That process is called integration. So integration is the inverse of derivatives, or the inverse of differentiation. So how do we do it? Well, before we learn the algebraic approach, we can do the geometric approach, which is using shapes. So we can do something called Riemann sums. And Riemann sums, basically all we're going to do is we're going to make rectangles, and we're going to find the areas of each of those rectangles. There's a couple different ways we can make those rectangles. We can make them going left. So you would start on the left-hand side and go this way. You could do a right Riemann sum, so you would start on the right side and work your way over. You could do a midpoint sum, which you would do in the middle of the 2 points. And then you can also do a trapezoidal sum, which instead of making rectangles, you would make trapezoids. So a left Riemann sum, what you would do is you would just start on the left-hand side of the graph, and you would make rectangles. So that first rectangle would have a height of 0, so there's going to be no rectangle there. The second rectangle, you would just start at a height of, it looks like 1, and then you would make a rectangle there. The next rectangle, so you would make the points on that blue curve, x squared, would have a height of 4, and then you could make the base 1. And then the next rectangle would have a height of 9, and then you would go over. So this would be a left Riemann sum, because you're going from the left, and then all you would do is you would find the areas of each of those rectangles and add them together, and that would be an approximation for the area under the curve. You could also do a right Riemann sum. So a right Riemann sum, you would start on the right-hand side of the graph, and you would make your rectangles starting with that right point. So this rectangle would exist here, and then the next rectangle would exist here, and then the next rectangle would exist here, and then that last rectangle would exist here. So notice the left Riemann sum in this case would be an underestimate because it's underneath the curve, and then the right Riemann sum would be an overestimate because all of those rectangles are over the curve. All right, so let's actually do these calculations on the slides underneath. So a left Riemann sum. So if we're going to do a left Riemann sum, it's exactly what I just said. So that would be my first rectangle. That would be my second rectangle. That would be my third rectangle. And that would be my fourth rectangle. And I'm doing each rectangle has a width of 1. I could have had them make them have a width of 1/2 or 1/4, etc. And we'll talk more about that next class. So my left Riemann sum with 4 rectangles, or we would say this 4 subintervals. So if they say 4 subintervals, they mean 4 rectangles. And the notation is we would do a capital L with a 4 subscript is equal to, and now you just find the area of each of those rectangles. Well, to find the area of a rectangle, you do base times height. The height of the rectangle is going to be the function value. The base is going to be the change in x. All right, so my height of this rectangle right here is 0, and then the base is 1, so it's going to be 0 times 1 plus, in my next rectangle, the base is 1 and the height is 1, so it'll be 1 times 1 plus, in my next rectangle, the base is 1 and the height is 4, so it'll be 1 times 4 plus, in my next rectangle, the base is 1 and the height is 9, so that rectangle would be 1 times 9. If you add all of those together, you get 0 plus 1 plus 4 plus 9, and you get 14. So the left Riemann sum approximation would be 14. So an approximation for the area under the curve would be 14 units using a left Riemann sum. All right, let's do the right Riemann sum approximation. So again, the area under the curve would be starting from the right. That would be my first rectangle. And then my second rectangle would be right here. And then my third rectangle would be right here. And then my last rectangle would be right here. So my right Riemann sum with 4 rectangles. And again, they'll call them 4 subintervals. And you can do capital R with a subscript of 4. So my right Riemann sum with 4 rectangles would be, well, in my first rectangle, the base is 1 and the height is 16. So it'll be 1 times 16 plus, in the next rectangle, the base is 1 and the height is 9. So 1 times 9 plus 1 times 4 and then plus 1 times 1. So this is going to be 16 plus 9 plus 4 plus 1, which would be 20 plus 10, so 30. So the right Riemann sum approximation for the area under the curve would be 30. So I know that the area under the curve is going to be somewhere in between 14 and 30 for the actual answer. The more rectangles that I make, so the more subintervals that I have, so if I shorten the width of each of those rectangles, the more accurate my answer will be. Let's look at a midpoint sum. So I said for the midpoint, instead of going from the left or the right, you would go in the middle of each of those rectangles. So right here, and then right here, and then right here, and then right here. So now that looks more accurate because part of the area is above the curve and part of the area is below the curve. So this is going to be a more accurate representation than the left Riemann sum or the right Riemann sum. But in order to figure out those heights, remember the height is the value of f of x at each of those points. Well, I need it at 0.5, 1.5, 2.5, and 3.5. And those are going to be the heights for each of my rectangles. So my midpoint sum with 4 rectangles or 4 subintervals is going to be, notation-wise, you do a capital M with a 4 subscript is going to be, now I need to find, so my f of x is x squared, so I want to find this at 0.5. So 0.5 squared would be 0.25. So it'll be 1 times 0.25 for the height. Then plus f at 1.5 squared. 1.5 times 1.5 would be 2.25. So this will be 1 times 2.25. Then plus f at 2.5 squared would be 6.25. So 1 times 6.25. And then plus f at 3.5 squared, just so I don't make a dumb mistake, 3.5 squared, I get 12.25. So 1 plus 12.25. And so that would be the area of those rectangles. So we would get 3, 9, 21, I believe. So the area under that curve should be closer to 21. So, and 21 is in between 30 and 14. So we're good. And then the last type is called a trapezoidal sum. So to make a trapezoidal sum, we're going to make trapezoids. So to make trapezoids, you connect one height to the next height and then come straight down. And then connect the first height to the second height and come straight down. And then first height to the second height and come straight down. And then first height to the second height and come straight down. So you're making trapezoids instead of rectangles. And notice that's even more accurate than the midpoint sum or the left-hand or right-hand Riemann sum. But now you need to remember how to find the area of a trapezoid. And to find the area of a trapezoid, the area formula is you take base 1 plus base 2 times the height and then divide by 2. So our trapezoids are actually sideways right now. So our trapezoids look like this. So this would be base 1, this would be base 2, and then the height is going to be the left and right portion of that. So we're going to do base 1 plus base 2. So in this first one, we're going to do 0 and 1. So it's going to be, so trapezoid with 4 trapezoids would be base 1 is 0, base 2 is 1, and then the height goes left and right, so times 1 divided by 2. Then plus in my next trapezoid, we have base 1 is a height of 1, and base 2, or sorry, not a height. Base 1 has a length of 1, base 2 has a height of 4, so it'll be 1 plus 4. And then the height of my trapezoid goes left and right, so it'll be 1 times 1 divided by 2. Then plus, in my next trapezoid, base 1 would be 4, base 2 would be 9, and then the height is 1. So 4 plus 9 times 1 divided by 2, then plus. We have 9 and 16 for the two bases, and then the base is 1. So 9 plus 16 times 1 divided by 2. And so if I work this out, I get 1/2 plus 5/2 plus 13/2 plus 25/2, which would be 6, 30, 43, 44, so 22. And so that would be as close to the actual area under the curve as we could get. And we already talked about the overestimates and the underestimates, so which ones are overestimates and which ones are underestimates. That trapezoid sum looks like it might be a little bit of an overestimate. The midpoint sum, we don't know if it's an over or an underestimate without looking at the actual integral or the actual area under the curve. In this case, the right Riemann sum would be an overestimate because those rectangles are over the actual area. And then the left